Let's do one more section on graphing rational functions. Our third section on graphing rational functions. Here we're going to graph y equals x squared minus 3x minus 4, all divided by x plus 2. Now, in this problem, unlike the problems that we did in part 2, the numerator really should be factored, not the denominator. So let's do that really quickly. This factors to x minus 4 and x plus 1. What's nice about this is that our vertical asymptotes are easy to see. Our vertical asymptote, is easy to see. That's just when x plus 2 is equal to 0. So we only have one vertical asymptote at x equals negative 2. Whoa. Little hiccup. There we go. I'll straighten that out while I talk about the next point. So now when we go to find our horizontal asymptotes, much better, we would notice that the degree of the numerator is actually bigger than the degree of the denominator. The degree of the denominator is only 1, but the degree of the numerator is 2. So there are no horizontal asymptotes. What we have instead are slant asymptotes, or a slant asymptote rather. So here's what we're going to do to find our slant asymptote. We're going to use long division. I'm going to do this color. Use long division. And if you haven't seen our video previously on long division of polynomials, please make sure you check that out. Here's what we're going to do. X plus 2 divided into x squared minus 3x minus 4. When we're doing long division, we look at the first term. So what do we do? Multiply x by to make it an x squared. That's x. Distribute the x through the x plus 2, so that would be x squared plus 2x. My students always, for subtracting, say draw the line and change the signs, leaving us with the x squareds canceling and negative 5x minus 4. Starting all over again, what do we multiply x by to make a negative 5x? That's negative 5. Distributing the negative 5 through the x plus 2 gives us a negative 5x minus 10. To subtract, drawing the line and changing both of those negative signs into positive signs gives us negative 5x's canceling and a remainder of 6. So plus 6 still needs to be divided by x plus 2. So here's what we just found. We just found that our y could be written as x minus 5 plus 6 over x plus 2. The slant asymptote, I'll highlight this in yellow, is given by the first part of the result after long division. So disregarding the remainder, the x minus 5 gives us our slant asymptote. So now remember, I want you to notice that's a line, y equals mx plus b, has a y-intercept of negative 5. So 1, 2, 3, 4, 5. And a slope of 1, so we'll go up 1 and over 1. And there is our slant asymptote. Okay, so just to recap that really quickly, if the degree of the numerator, 2, is bigger than that of the denominator, 1, then you could have an oblique, or sometimes called a slant asymptote. The way you want to figure out what the equation of that slant asymptote is using long division. Okay, once you get the graph of y equals x minus 5, you can ignore the remainder because the bigger that x gets, the less and less important this 6 over x plus 2 gets. So now we can finish our problem by finding our intercepts and some more points if we need to. So going back to the blue pen, let's see, to find the y-intercept, we're going to let x equals 0. So this would be y equals, I'll plug it into the first part of our function here. So 0 minus 3 times 0 minus 4 over 0 plus 2, which gives us negative 4 over positive 2, or negative 2. So we have the ordered pair 0, negative 2 for our y-intercept. Okay, 0, negative 2 is right here for our y-intercept. Okay, finding the x-intercepts. To find the x-intercepts, we're going to set y to 0. So we have 0 equals x minus 4, x plus 1 over x plus 2, just choosing to do the factored version of our function. Multiplying both sides by x plus 2 gives us 0 equals x minus 4, x plus 1. So our two x-intercepts are x equals 4 and x equals negative 1. X equals 4, 1, 2, 3, 4. Remember, if this is y equals x minus 5, x equals 5 is that point right there. And x equals negative 1 is right there. So here's one thing that we know. Now we know these 2 points, 4 and negative 1, are the only 2 points where our graph will cross the x-axis. And since our graph has to behave according to those asymptotes, the graph will look something like this. Okay, now I know the graph can't also be down here because that graph would fail the vertical line test, intersecting in 2 different spots. So I know the graph doesn't look like that. So let me get rid of those lines. I just don't know on the left-hand side whether the graph is in that section or the section below it. So in order to figure that out, I'm going to pick one more x value. So when we're plotting more points, I'm going to pick something like x equals negative 3, anything over here to the left of negative 2. And I think I'll plug this into the factored version just for the sake of arithmetic in my head. So negative 3 minus 4 times negative 3 plus 1 over negative 3 plus 2 gives us negative 7 times negative 2 over negative 1, which is a negative 14. So when I have x equals negative 3, I'm way down here at negative 14 in this region. So I know my graph looks something like that. I don't know that the top of this graph right here is precisely at negative 14, so I hope I didn't give that impression. I just know that the graph is down here below in the bottom portion of this graph on the left-hand side. So I know that the graph looks, let me erase this so I don't make it quite so, actually, I'll draw that back in there. But what I don't know is I don't know exactly how that looks. So there, I just know it's in that section. It's a little bit better. If I wanted to get a really accurate graph, I would graph more points, but I just wanted a rough sketch of the graph. Let's try one more of these. Okay, let's graph y equals x squared plus 3x plus 2, all divided by x minus 1. Just like in the last example, I'm going to factor that part that can be factored. So the numerator factors to x plus 2, x plus 1 over x minus 1. And I can use either version of the function y depending on what I'm doing. So for finding vertical asymptotes, both are really nice. Just looking at that denominator, my only vertical asymptote is at x equals positive 1. So I'll label that. Okay, Just like in the last example too, the degree of the numerator is 2, which is bigger than the degree of the denominator. So since the degree of the numerator is bigger than the degree of the denominator, then I have no horizontal asymptote. What we do have, again, is a slant asymptote because the degree is bigger in the numerator than it is in the denominator. So, just like in the last problem, I'm going to use long division. Okay, so we've got x minus 1 divides into x squared plus 3x plus 2. So just looking at the first two terms, x multiplies by x to make an x squared. Distributing that x through, we've got x times x is x squared, x times negative 1 is negative x. And then we'll draw the line and change the signs. Okay, the x squareds are going to cancel. 3x plus x is 4x. And bringing down the plus 2, we start all over again. So what we multiply x by to make it a 4x is a 4. Distribute the 4 through, so we have 4x minus 4. To subtract, draw the line and change the signs. So the 4x's cancel, and we're left with a remainder 6. So plus 6 divided by x minus 1. So our y is equal to x plus 4 plus 6 divided by x minus 1. And after doing all that long division, remember, our slant asymptote is the first part of that without the remainder. So now we need to graph y equals x plus 4. That's a line. The y-intercept is at 4. Slope is 1, so from 4 up 1 over 1 puts us here. Cool, and there's a rough picture of what our graph looks like for our asymptote. Make that a little bit more dashed. That's better. Okay, finding our intercepts. Let's plug in for the y-intercept. Let's plug in our x equals 0. And we're going to get y equals 0 squared plus 3 times 0 plus 2 over 0 minus 1 gives us negative 2. So our x-intercept is at x equals 0, y is at negative 2. That is really helpful. That tells me that my graph has to be in this lower section down here. I'll keep finding the x-intercepts. So to find the x-intercept, we're going to set y equal to 0. 0 equals x plus 2, x plus 1 over x minus 1. And multiplying by the x minus 1, we just get 0 equals x plus 2 times x plus 1. So our two x-intercepts are at negative 2, negative 1. Negative 2 and negative 1. Remember, if this is x plus 4, this is at negative 4. So here's what our graph looks like. Something like that. Great. Now I know that the graph can't be up here. That would fail the vertical line test and wouldn't be a function. But I don't know on the right-hand side whether the graph is in the top section or the bottom section. So I'm going to pick a number like, I don't know, something to the right of x equals 1, x equals 2 as my more points so I can figure out where my graph is. So let's figure out where we can plot x equals 2. I can choose to plug it into the first version or the factored version. I'm going to choose the factored version just because it's easier with the arithmetic. So 2 plus 2, 2 plus 1 over 2 minus 1 is 4 times 3 over 1 is 12. So I have x is 2 and y is 12. That is way up here. So that tells me the graph is in the upper section. I don't know exactly how far down it goes to get down here. I just know that it's in the upper section. I could plot more points if I really wanted to, or use calculus, but we just want a rough sketch. I want to finish this lesson with two more problems that look really similar to the previous two problems that had oblique asymptotes. But they are different, very different. They don't appear to be different, but watch what happens once we start the first step, which is to factor. So factoring our numerator, we've got x minus 4, x plus 1 over x minus 4. This has never happened before in the problems that we've been doing. The x minus 4, which would normally be our vertical asymptote, give us where our vertical asymptote is, it cancels. So we have a really interesting thing happening here. We have x plus 1 in the numerator is the only portion of our graph remaining. So our graph must resemble the line y equals x plus 1. But from the domain, x cannot be equal to 4. So this is a really important point. If you have canceling that happens like this, and it cancels out what would have been your vertical asymptote. So if this cancels, what you have is a hole in your graph at what would have been that point. So we have the line y equals x plus 1 with a hole at x equals 4. So we have the graph y equals x plus 1. So let's see, that has a y-intercept of 1 and a slope of 1, up 1 over 1. So drawing that line in, that's similar to what our graph looks like, but we have this hole that cancels from the canceling that happened at x equals 4. So I would like to figure out where that hole happens. So at x equals 4, we have y equals 4 plus 1. Y would be equal to 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. So right here, where we would normally have an asymptote, since our asymptote canceled, but x still can't be equal to 4 from our domain, what we have instead is a hole in the graph. This is kind of confusing, but kind of wonderful. We don't have any horizontal asymptotes. We don't have any vertical asymptotes. We can still find the the intercepts in more points, but we just have a line right here with a hole in it. Graphs where canceling happens and the vertical asymptotes go away, what we're left with is a hole at a certain point, are really common in calculus. So let's try one more of these graphs before finishing the lesson. Last example. Let's graph y equals 5x squared plus 5x plus 6, all divided by x plus 2. And if I go to factor this like I've been doing, the numerator factors to x plus 3 and x plus 2 over x plus 2. So before I get excited and I say that I've got a vertical asymptote at x equals -2, since the x plus 2 cancels away, I don't have a vertical asymptote there. We have a hole at x equals 2. And the leftovers from our function, which is just y equals x plus 3, is all we need to graph, just making sure we represent the hole in there as well. So let's see, y equals x plus 3, y-intercept is at 3, slope is 1, up 1 over 1. Graph our line, sort of. And then going to x equals -2, we would have a hole at x equals -2. In the last example, I figured out exactly where that ordered pair was. And to do that, you would take your x equals -2 and plug it into your either function, the top or the bottom. Oh, I'm sorry, only the bottom function. So plugging it in here, -2 plus 3 is 1. So this must be, oh, that's pretty close, at y equals 1. And I don't have to worry about horizontal asymptotes. I don't have to graph the intercepts. I already graphed the y-intercept, and I don't have to graph any more points. I'm all finished.